Hello. In this video, we're going to look at Fermat's theorem. So in the last video, we talked about minimums and maximums, and we began to think that, well, these relative minimums and relative maximums seem to be happening where there are horizontal tangents. And in fact, Fermat's theorem confirms that this is true. So let f be a function and c be a number in the domain of f. If fx has a relative minimum or a relative maximum at x equals c, and f prime c exists, then f prime of c has to equal 0. You can imagine this if you were going to draw yourself some type of maybe valley for a minimum or some type of hill for a maximum. Right at the very top of that hill or right at the bottom of that valley for a minimum or a maximum, the tangent line is definitely going to be horizontal. There's no way around it. That's how it's going to look. And so Fermat's theorem proves that for us, that the tangent line is equal to 0. The derivative is 0. It's horizontal when you have a minimum or a maximum. So we're going to look at the proof of this. And we're going to assume a relative minimum. If you look at your textbook, you can see the proof for the relative maximum. It's very similar, but we're just going to prove the one of them in this video. So we're going to do the proof. Suppose fx has a relative minimum at x equals to c. Well, we have to then think, okay, that's the English definition, but what does the math say? What do we get when we have a relative minimum? And if you remember, a relative minimum means you have an open interval. So we can say, then there exists an open interval AB containing C such that, well, what happens in this open interval? If you remember, because we have a relative minimum, it means that f of c is less than or equal to f of x for all x in the interval a to b. F of c, since it's a relative minimum, is the lowest point around. So we have our valley example, like here. So if this is our c, f of x is always going to be greater, or f of c is always going to be less than f of x for all x in the interval a to b. Now, we need to somehow begin to talk about the derivative. And so what we're going to do is, looking at this relative minimum example we have up here, if we call this point here c, well, this is our interval a to b. And any other point in here you could call x. But x and c and a and b, you begin to have too many letters. And so in particular, we're not going to call that point x. We're going to think about moving over a little bit away from c. We'll move over a distance h. And so if we're going to move over to the point x, we could think about it as going c plus h. You start at c and you move a little bit over, and so you move h away from c. Now, what this means is that we could rewrite this inequality we have here. We could say f of c is less than or equal to, instead of f of x, we're going to put f of c plus h. Again, this is the same thing as x, but we've labeled x in terms of its relationship to c. X is h away from c, so it's c plus h. And then another way to write this inequality, if we move f of c to the right-hand side, is 0 is less than or equal to f of c plus h minus f of c. All right, if you look, we're beginning to build a derivative here. F of c plus h minus f of c, the next step would be to do over h. But when you divide by h, h might be positive as you move to the right of c, but h might be negative as you move to the left of c, which means we are going to be dividing by a positive or negative number. And inequalities, they flip when you divide by positive or negative. Well, I should say they don't flip when it's positive, but they do flip when it's negative. So we need two cases. So we're going to first consider h greater than 0. Then if we divide the inequality here, we'll have 0 over h is less than or equal to f of c plus h minus f of c over h. Because the inequality doesn't flip when h is positive. And if you look at this, the left-hand side is just 0, because 0 divided by anything is 0. So we'd have 0 is less than or equal to almost our derivative. So let's go ahead and do the derivative. So to do the derivative, hence, we need a limit. And we can say the limit h approaches 0, we'll do the limit of the left-hand side. H is going to 0 from the right, because h is positive. So the limit of 0 will be less than or equal to the limit h approaches 0 from the right of f of c plus h minus f of c over h. Now, this right-hand side here, this right-hand side is the definition of the derivative with h coming from the right-hand side. And so, since the derivative exists, we know it exists, that's part of the proof, we're assuming that f has a relative min and the derivative exists. So that means this limit here has to exist. And so since the derivative exists, the derivative here has to be greater than or equal to the limit of 0, and the limit of 0 is 0. So we could say, since f prime c exists, 0 is less than or equal to f prime of c. Again, this is the derivative, but instead of x plus h minus fx, it's c plus h, so it's f prime of c. Now, let's go ahead and consider the other case. So, we're going to consider if h is less than 0. Well, then we can still divide our inequality that we started with, but we'll have 0 over h is going to be greater than or equal to f of c plus h minus f of c over h. Because when you have a negative number, it flips the inequality. So we could do the limits, and we get the limit h approaches 0 from the left of 0 will be greater than or equal to the limit h approaches 0 from the left of f of c plus h minus f of c over h. Again, since f prime of c exists, this tells us that 0 will be greater than or equal to f prime of c. Well, we just showed here that f prime of c is greater than or equal to 0. And here we're showing that f prime of c is less than or equal to 0. Well, what number is both greater than or equal to 0 and less than or equal to 0? There's only one number, the number 0. So these two inequalities tell us that therefore f prime of c must be exactly equal to 0. And we're done the proof. Now you can see the textbook for the relative maximum version of this proof. Everything is very similar. There's just a few inequalities that flip around. But this definitely shows that the derivative must be equal to 0. Alright, it's time for a new definition. We're going to define a critical number. Now a critical number is, well, a number c in the domain of fx is called a critical number if either f prime of c equals 0 or if f prime of c does not exist. So anytime you either have a derivative of 0 or a derivative that doesn't exist, you get what's called a critical number. Now let's look at this graph. Let's see if we can find the critical numbers. Well, right about here, it looks like we have a horizontal tangent. We have a derivative of 0. So that looks like a critical number. Right about over here, we have a critical number. Right about over here, we have a critical number. Over here, well, we don't have a derivative of 0. The derivative here does not exist because it's a sharp point, if you remember. And so that makes it a critical number. And right here, again, the derivative does not exist. So we have 1, 2, 3, 4, 5. Oh, wait, there's one other critical number right here. If you think back to the graph of different things from pre-cal. You might have remembered how the graph becomes sort of flat near the axis. This graph here that becomes flat right around there, it has definitely a derivative of 0. It's hard to visualize, but there's definitely a horizontal tangent right there. It's pretty hard to draw right about there. The graph does have a derivative of 0. Now, interesting on the critical points, if you notice, this is a relative maximum, this is a relative minimum, relative maximum, relative minimum, relative maximum, but this point right here is not a max or min. This is not a max or min, and that's very important. We're going to look at this in more depth as we go throughout these examples, but just because you have a critical number does not mean you have a minimum or maximum. Fermat's theorem is very precise, and this is, again, it goes one way, but it doesn't go the other way in mathematics. A relative minimum or maximum has to occur at a critical point, or a critical number, but a critical number is not necessarily a minimum or maximum. Now, let's look at a method for finding the critical numbers. To find them, we're going to use the following steps. Step 1, we're going to write the domain of fx. Critical numbers only come from the domain, so we need to know what the domain is. Step 2, we're going to find f prime x, set f prime x equal to 0, solve for x, and keep the values which are part of the domain of f. Step 3, we're going to find those values of f where f prime is undefined. We're going to keep those values which are in the domain of f. So it's basically find the domain, set the derivative equal to 0, and then look where the derivative is undefined. So let's do an example. Let's find the critical numbers of fx equal to x cubed plus x squared minus x. Well, step 1, we'll find the domain. And the domain looks like, well, minus infinity to infinity are all real numbers. It's just a polynomial, so it's defined everywhere. Step 2, let's find the derivative. 3x squared plus 2x minus 1. And then we need to set this derivative equal to 0. Well, this requires us to use some pre-cal knowledge. We're taking a polynomial and setting it equal to 0. We need to do some factoring, so pause the video, see if you can find a factoring for this polynomial. So hopefully you came up with something like this. 3x minus 1 and x plus 1. So that tells you that x is equal to 1/3 and x is equal to -1. So both of these will be critical numbers. For step 3, this derivative here is never undefined. There's no 0 in the denominator. There's no roots or anything. There's never any issues there. This is always defined. So 3 is going to be not applicable. So let's take a quick look at this on Desmos. So we can see here our polynomial. It's a nice cubic function. And if we look right here, you can clearly see a derivative of 0 at -1 and another derivative of 0 at 1/3. Now again, if you were thinking back to pre-cal and you were wondering, how do we find those little peaks and valleys on polynomials? Well, hopefully your teacher mentioned that you need to use calculus, and now we're beginning to see how this would work. The peak and the valley here are going to be where the derivative is 0, their relative maximum and minimums, and we find those by first finding the derivative and then setting it equal to 0. So a nice connection there that we'll begin to explore more in future lessons. Now let's look at one that's a little bit nastier. This one has some weird powers. It's not a nice polynomial. We have fraction powers. But we can still find the critical numbers. So step 1, let's find the domain. Now because these are both 3, they're cube roots. Square roots are bad. You can't necessarily find the square root of every number. You can't find square roots of negative numbers. But you can find cube roots of any number. So the domain is actually -infinity to infinity. Now let's try to find that derivative. This is going to be a little bit more challenging. So we're going to use the power rule at first. So f prime x will be equal to 5. We bring down the 2/3. X to the, well, this will be -1/3 plus 5 over 3 x to the 2 over 3. Now, we need to set this equal to 0, and to do that, we're going to need to simplify this derivative. We're going to need to combine things and make the powers not negative. We're going to need to do a lot of algebra here, but the goal is eventually to set this equal to 0. So the first step is to do the derivative. Now we have to simplify. So 5 times 2 will be 10, so 10 over 3. The negative can move down to the bottom, so x to the positive 1/3 in the bottom, plus 5 over 3, x to the 2 over 3. Now we need to make these probably look a little bit nicer, so I'm going to turn them from fractions into actual radicals. So this is 1 over 3, or 10 over 3, sorry, cube root of x, plus 5, and then here we have the cube root of x squared over 3. And so we'll keep on going with this. This will give me, well, I need to do a little common denominator, so let's multiply this one by cube root of x, cube root of x. So that will give me 10 plus 5. Well, what's the cube root of x squared times the cube root of x? We should probably work that out over here. So this is going to be x to the 2/3 times x to the 1/3. When you have the same base, you add the powers, so 2/3 plus 1/3 is 3/3. So just x. Oh, that's pretty nice. So we get 5x over 3 cube root x. Alright, I think we're ready. We can set this thing equal to 0. Now a fraction is only 0 when the top is 0, so that means that 10 plus 5x must be 0. Or x has to be equal to -2 if we move the 10 over and then divide by 5. So there's our first critical number, x equals to -2. But step 3 is definitely going to be valid here, because if you look at that derivative, there's a denominator there. And if you have a denominator, chances are you have a value that's going to give you 0. In particular, we're going to set that denominator equal to 0 to see what value we need for x. So we go 3 cube root of x equal to x. So we can divide by 3 and get the cube root of x equals to just 0. And then we cube everything, so x equals 0 cubed if you want, so x equals 0, which you might have noticed right away. But x equal to 0 is another critical number, because that will make the derivative undefined. So we have two critical numbers, x equals to 0 and x equals to -2. This one comes from making the derivative 0, this one comes from making the denominator 0, which makes the derivative undefined. Again, let's look at this on Desmos. So here we have a very interesting graph. It looks almost like a parabola on the left-hand side, and then it shoots off on the right-hand side. We can see here the derivative is clearly 0. We have a horizontal tangent at -2. And at 0, we can see the derivative is undefined because we have that sharp point. So again, both of those are critical numbers, and we can see those critical numbers very clearly on the graph. They look so obvious. The horizontal tangent line is so clear, and the derivative, where it's undefined, just jumps right out at you. So here we have a quick multiple choice question. Which of the following is not a critical number of fx, given that f prime x equals x minus 1 times x minus 2 over x minus 3? So pause the video and give it a try yourself. Alright, let's take a look. The critical number, if you remember, a critical number has to make the derivative 0 or the derivative undefined. Well, if we plug in x equals 1, 1 minus 1 will be 0, and so overall the derivative will be 0. If we plug in 2, 2 minus 2 will be 0. If we plug in 3, 3 minus 3 will be 0, and that will make the derivative undefined. So for this one here, f prime of 1 is equal to 0, f prime of 2 is equal to 0, and f prime of 3 is undefined. So all three of those are critical numbers, which means the answer is A, x equal to 0. That is not a critical number. So let's try some more examples. Let's find some more critical numbers. In this case, we have an absolute value function. We have fx equals absolute value of 2x plus 3. So we'll go through the 3 steps again. Step 1, we'll find the domain. Well, it's an absolute value function, so the domain is just going to be minus infinity to infinity. Step 2, we should look at the derivative. Well, the derivative of an absolute value function, in this case, we should write this because it's a piecewise function. So we're either going to have 2x plus 3 or negative 2x plus 3. And this is going to be when x, if you work it out, is greater than or equal to negative 3 over 2. Or when x is less than negative 3 over 2. Okay, so when we go to do the derivative then, we can just think about doing the derivative of each one of these pieces. So the derivative of 2x plus 3 is just 2, and the derivative of negative 2x plus 3 is going to be negative 2. So f prime x looks like either 2 or negative 2. Just doing the derivative of each one of these linear functions. And then it's going to be when x is greater than, no equal sign anymore, it'll be greater than 3 over 2 or less than 3 over 2. Because if you remember, the derivative is undefined at that sharp point on the absolute value. So it's pretty clear here, f prime of x is never 0. So we don't get a critical number from that, but f prime of 3 over 2 is undefined. So that gives us our critical number, x equal to, sorry, that should be negative. F prime of negative 3 over 2 is undefined, so that gives us our critical number at x equals negative 3 over 2. So let's look at another example here, this time involving a trig function. So let's find the critical numbers of f of theta equals 4 theta minus tan theta on the interval 0 to 2 pi. So step 1, we've got to look for that domain. So if you remember, for tan of theta is undefined. So theta is not going to be equal to pi by 2, because tan of pi by 2 is undefined. And then, well, technically negative pi by 2, but that's not part of the domain. We're only looking at 0 to 2 pi. So the other one would be 3 pi over 2. All right, let's just find the derivative. Step 2. F prime of theta will be equal to, derivative of 4 theta is just 4. Derivative of tan theta is secant squared theta. We're going to set this equal to 0, so we've got a factor. So 2 minus secant theta, 2 plus secant theta, doing a little difference of squares there. So this gives us secant theta equal to 2 and secant theta equal to minus 2. So we can flip that into cos. So cos theta equals 1/2, or cos theta equals negative 1/2. So using our unit circle knowledge, cos of theta is equal to 1/2. Well, that's going to be at pi by 3. And we're also going to get one at 5 pi by 3. Over here, we would get theta equal to 2 pi by 3. And theta equal to 4 pi by 3. Now, step 3, what about f prime being undefined? So 3, where is f prime of theta undefined? Well, that would mean looking back over here, 4 is not ever undefined, but secant squared is really 1 over cosine. So we'd have 4 minus 1 over cos squared theta. And so it's possible that the denominator could be 0. It would be 0 where cos of theta would be equal to 0, which means theta would be equal to, well, pi by 2 and 3 pi by 2. But of course, these are numbers, if you look back, they're not in the domain. So these have to be rejected because they are not in the domain. So our critical numbers are these four here. Let's do a multiple choice question. The critical number for the function y equals 4x squared plus 6x plus 3 is, give it a try. Well, we'd have to find the derivative. So we'd have to go ahead and find y prime, which would be 8x plus 6. Set it equal to 0. 8x equals negative 6. X equals negative 6 over 8, which is negative 3 over 4. So the answer would be A. This is our critical number. Let's try another question. If C is a critical number, then f prime of C equals 0. Is that true? Is that always true? Is that sometimes true? Is that never true? Or are you not sure? Let's think about it. Is f prime C, if f prime C is 0, does that make sense? And pause the video, give it your best shot. Okay, if C is a critical number, then f prime of C is 0. Well, the definition of a critical number is that f prime of C is equal to 0, or f prime of C is undefined. So if we have a critical number, we don't necessarily have the derivative being 0. Sometimes the derivative is 0, but sometimes the derivative is undefined. So this is sometimes true. If f prime C is equal to 0, then C is a critical number. Oh, it looks like we've reversed the statement. Is this always true, sometimes true, or never true? All right, well, if f prime C is equal to 0, then of course this is always true. This means that C is a critical number. So this is always true. It fits the definition. A critical number, again, a critical number is where the derivative is 0 or the derivative is undefined. And so if the derivative is 0, well, certainly that's one of those options. And so then it will always be a critical number. Now, one last thing we're going to look at here, using the definition of critical numbers in Fermat's theorem, if a function has a relative min or max, it must occur at a critical number. However, not every critical number corresponds to a minimum or a maximum. Now, this is what we mentioned earlier in the video, but we need to look at a concrete example here to hammer this point home. So let's look at the function y equals x cubed. Well, we could find the derivative. We could set it equal to 0, and so that would give you x equal to 0. So therefore, this is a critical number. Critical number. And on a graph, you could see that. If you remember graphing the cubic, it's got to slide along when we get to the axis here. It should look something like this. So it's got to flatten out and slide along and then keep going. So right here, at x equal to 0, we have a derivative that is flat. We have a horizontal tangent line. So clearly we have a critical number, but not a relative min or relative max. And this is very, very crucial. Every minimum or maximum happens at a critical number, but not every critical number will be a minimum or maximum. It doesn't go both ways in mathematics. And this example clearly shows where we have a critical number, but we do not have a relative minimum or a relative maximum. So for homework, make sure you try questions on page 283, numbers 29 through 44. Thanks for watching.